Now that we have described our random variables, now it is time to introduce the probability distributions. Probability distributions are nothing but functions that we can make use of all of our skills that we acquired during our undergrad years learning calculus and algebra. And here we go. But before we move on to probability distributions, we need to discriminate between discrete random variables and continuous random variables, because the math that follows the distinction has some a little bit differences. So for discrete random variables, we're talking about the values of x. So both discrete and continuous random variables, they're both described with capital X, and these little x's, if these little x, the outcomes are taken values in discrete different points, they are actually not in real numbers, but they are one of the different discrete set of numbers, right? So it can be anything -2, -1, 0, 1, 2, yada yada yada, right? So we're talking about discrete random variables. They're taken discrete numbers, and we discussed we have a definition of probability of x equals little x, and this is we discussed that this is a probability distribution, and there is a name for this function. Now we can make it into a function. We can store all the probabilities that we can have for each and every one of these outcomes, namely this function that we will represent with a p, and this p will have the subscript capital X here, and the argument for this x is going to be lowercase x, and that's going to keep in memory the probability of capital X taking the little x, right? So this function will have other probabilities of each and every one of these x's. So this is a function in the domain called the discrete random variables. The discrete values, say I have all of the x's, and for all of the x's I will keep probability of x given x, and these are going to hold in memory what's the probability of each and every one of these events are, right? So they can be 0, etc. So this is what the function is, and there's a name for this function, and the name for this function is probability mass function. In short, it's PMF. And throughout the course, we will keep referring to this as distribution. So it's the distribution of probabilities among all the possible values, right? So there are some axioms associated with the probability mass functions. There are following the probability axioms. First of all, nothing can be negative probability, right? And nothing can be more certain than 100%. So we know that P of x will have to be less than or equal to always 1 and greater than or equal to 0, right? So that's the first axiom. And the second axiom is that we know that if we sum all of the probabilities of the space of possible outcomes, we will get to the number 1. So if I sum over all of the x's, P of x, and this number is guaranteed to be 1. There is one more function that's particularly defined that's going to be even more useful when we're dealing with continuous random variables in a second, and that's the cumulative distribution function. And cumulative distribution function takes the letter capital F, and it's also described with this subscript that describes the random variable that is talking about, and its argument is always the outcome. And cumulative density function is talking about the probability of, is defined by, let me also put this triangle on top of this equation here, is defined by probability of x less than or equal to x. So it's not only holding the value probability of x equals x, but also talking about, but is also representing the probability of all of the little x's up until the x, right? So in theory, you can get the f of x from p of x by, so f of x is nothing but sum all of the x's from negative infinity to x, probability of x of x. So maybe I should change the index of this inside x. So I should call maybe x tilde, and I should make this x tilde. So that's the definition of cumulative density function, and so it's short for CDF. Why did I introduce this CDF that we will never use? Just so that I can introduce the continuous random variables. So when the random variables is continuous, it can take any number. So x is in real numbers. So it can take any real number that you can imagine. So therefore we're talking about a p x of x is not necessarily is not equal to probability of x equals x. So that's one giant rule that I would like to share with you, because when we're talking about the probability distribution function, again the density for continuous random variables, it is going to again look like it's also defined in the domain of x, and it is going to represent, let me draw our Gaussian distribution that we're very accustomed to. So it's going to look like probability of x, but each and every one of these values, let me take a thinner pen and take some other color. So this little x here is almost never observed. Even if it is probable, the exact point is never observed. So that's it. That's a deal with the physical quantities. That's a problem with exact observing the exact x, right? So we strictly speaking, we do not define probability of x is never probability of x equals x, but we know that we can define f of x, the cumulative distribution function, and it is in fact defined as probability of x less than or equal to x. So we can talk about the probability under this curve. We can calculate this area, and we can associate the probability here, and this is exactly how it is defined. And again, this is our CDF, and the relationship between p PDF, probability density function, and CDF is just that it is its derivative. So probability of x is defined as d over dx f x. So this is a probability density function, right? So probability density function does not directly tell you the exact probability of that exact incidence, which is continuous. And let's wrap our brains around what might be continuous random variables. We're talking about time. We're talking about space. We can be talking about other physical quantities like voltage, right? Or some signal level, some amino acid level, right? Some antigen that you can measure. Anything that you can measure, it is almost impossible to expect it to be measured once again, exact number, right? Even if let's take our timers, right? You know that it is actually practically discrete. Nothing is simulated by computers are actually continuous. But that's a topic, that's a philosophy for some future time. But if you, let's say, you stop your timer at some particular second and milliseconds and etc., so there's a probability that you can land there. And if you try to stop your timer exactly at that location, you will fail. It's almost impossible for you to land there. And just to conclude, the same axiom also exists for continuous random variables. So we can talk about probability of x, and it's always greater than 0. 1, we know that it has to be always greater than 0. And 2, by the way, it doesn't need to be less than 1, because all we need to do is the area under the probability density function, probability of x dx, this is 1. So we can, in theory, have a probability density function such that any particular point in this probability density function can be greater than 1, but the integral can be equal to 1, and it is always equal to 1. So this is mostly what we refer to as PDF, and it's probability density function. But good news, we will be referring to this as distribution too, right? So when we talk about distribution, when we say distribution, we will talking about probability of x.